Well, hello. My name is Evan Reese, and on behalf of the U.S. Resiliency Council and series sponsor Optimum Seismic, welcome to this seventh program in the Resilience Advantage webinar series. We hope you've enjoyed our previous episodes, and you can access them online at any time through the USRC or the Optimum Seismic website. The U.S. Resiliency Council is a nonprofit organization founded 10 years ago working to improve community resilience one building at a time. We use building performance rating systems, educational programs such as the Resilience Advantage, and coalition building with key stakeholders to make our built environment, your buildings and homes, more sustainable, prosperous, and resilient. Today, we go under the hood to look at how science and innovation are making resilience more achievable and more affordable than ever. Whether it's research being done at our leading universities and government-sponsored organizations, or technologies being developed by both startup and established companies, the entrepreneurial spirit we often see in high tech is alive and well in the structural engineering and construction industries as well. It's my pleasure now to introduce one of our champions for this episode, Dr. Ross Stein. He's the founder and CEO of Temblor in Menlo Park and has for decades been a leader in the development of earthquake engineering science. Ross, thank you so much for joining us today. Why don't you please tell us a little bit about yourself, about Temblor, and what you'll be demonstrating for us today?
Well, Temblor is a company that provides catastrophe models for the insurance industry and also provides a free public app and a news service about earthquakes that works everywhere in the world. And we have 100,000 people who use the app or read our articles every month. So our goal is to let everybody understand what their seismic risk is, no matter where they live, and inspire them to reduce it. And along those lines, let's start here. This is a building that you'll find anywhere in the world. We build buildings out of stacks of cubes, which is an incredibly stupid idea, but we like to put people in closest packing configuration. Now, no matter how well this building is bolted to the ground, which is a very good thing, no matter how strong you make the columns and the beams, also good things, this building is only as strong as its corners. And what an earthquake is going to do is shake this building from side to side. Also, earthquakes produce torsional motions that twist the building. And you can see how weak this building is. Now, if any one of these corners breaks, this building is probably coming down. And the problem is that a cube has no structural integrity. And if we want to be technical about it, we'll call it a tetrahedra. And if you don't believe me, look at this. IKEA house. Just put it in the back of your station wagon and drive it home. Okay, so there's what we want to avoid. Now I want you to see this. This is the exact same building. All I've done is snap these little corner braces in, literally snap. I'm using sewing snaps. And I have these little triangular corner braces. And in structural engineering, triangles are good and squares are bad. Now look. Nothing. This building will survive an earthquake without a problem. This is a disaster. Now let me ask you a question. How much more does it cost to build this building than this building? The answer is a few percent. The cost, let's say, of a half bathroom. It's incredibly low. If it's a retrofit, if it's an older building that needs to come up to this standard, maybe it's double that. But it's literally a small amount. A year ago, when we were refinancing our home, a California accredited appraiser came over to evaluate the value of our home. And I said, Fred, do you want to know whether or not our home was seismically retrofit? And he said, no. So what do you mean no? He said, but have you put any granite countertops in to any bathrooms? Okay, there's the problem in a nutshell. We would all love to have a nicer half bathroom, but this is really going to be the difference between surviving an earthquake and thriving and it being a disaster. And that's what we have to avoid. And we know how to do this. In a concrete building, the corners are strengthened in a different way than a wood building, but there's lots of techniques to do this for old buildings and to build new buildings better.
Ross, thank you so much. That was wonderful. I don't suppose you all expected that you would get demonstrations here today, but Ross, well, he captures a couple of things in what he said. First, and I think, most important, he captures how to communicate science and innovation that's developed in the engineering and seismology community and make it accessible. Make it understandable. I think whether it was that demonstration or the cost that he mentioned about, what it takes, that just an extra couple of percent, and that's something we've been talking about in previous episodes of the Resilience Advantage. That's something that people can understand. And of course, the other thing he does is he gets the science right? I mean, we have spent decades and decades following earthquakes, using our computer technology and our testing technology, some of which you'll learn about today in our episode, showing how the performance of buildings, can be improved and achieved, just like Ross says. So thank you, Ross, for that today. I would like to also start by thanking our major partners for the Resilience Advantage series. This is an important slide. I want you to know that these partners, the LA Chamber of Commerce and the LA County Business Federation, the Economic Development Corporation, plus, of course, the U.S. Resiliency Council and Optimum Seismic, are here to assist you, to give you additional information. Contact any of us. We're all committed to promoting resilience, and we can be good partners with you, whether you're a public or a private entity, in looking at how to grow your resilience of your organization. And then we'd also like to thank our series champions. We've had several champions over the past 7 months that have really made a special effort to promote the Resilience Advantage series. Tembler, of course, is our series champion for this month. And so again, a special thanks to Tembler and Ross Stein and his crew over there for sponsoring and championing our episode. So with that, I would like to make one other thank you too. You're about to see our 7th episode of the Resilience Advantage series. Each of these episodes is produced by Compassion Unlimited, a production outfit that has just been fantastic in bringing this all together in ways that are accessible, understandable, exciting. So again, thank you to David and his crew for all the work that you've done. So with that, we're going to just jump right in and start our episode, our 7th episode of the Resilience Advantage, this one on the science and innovation of resilience.
Welcome to the Resilience Advantage series, brought to you by the U.S. Resiliency Council and Optimum Seismic. I'm your host, Evan Reese. In this series, we're exploring what resilience means to the long-term sustainability of our communities in the face of natural disasters like earthquakes, hurricanes, floods, wildfires, and now even pandemics. Civil engineering is often considered the oldest engineering discipline. I mean, people were building buildings thousands of years before cars, airplanes, and computers. But that doesn't mean civil engineering and building construction isn't at the cutting edge of science and innovation. In this episode, we'll explore how engineers, researchers, and construction industry leaders have developed innovative solutions to make our buildings more resilient to natural hazards like earthquakes, and do it affordably. In the profession of earthquake engineering, experience is often the best teacher. This means learning what went right, and unfortunately also what went wrong when our cities are hit by large earthquakes. Thanks to science and innovation, instead of always chasing behind the last problem, we've learned to approach innovation from both directions, learning from the past and testing and modeling new designs for the future. And that has created new opportunities from which owners, businesses, and communities can now benefit. How this is being done and what these opportunities are what you'll get a taste of in this episode. The first advance we're going to talk about is the art and science of testing different structural systems and their components. to better understand those that present the greatest risk and how to build better. Tara Hutchinson is a professor of structural engineering at UC San Diego, and she runs the country's largest outdoor earthquake shake table. Tara, tell us a little bit more about what you do.
The lion's share of my research is in the general field of earthquake engineering. I'm an earthquake experimentalist, I would say, testing components, subcomponents, materials, and connections to try to better understand their performance under earthquake loads.
As I understand it, you can test full-scale mock-ups of buildings on your shake table.
You sure can. On our outdoor shake table, you can test a whole building on that outdoor shake table. You can test models of whole buildings on some of our indoor testing facilities.
Tara, why is it so important to do physical testing rather than just, say, modeling buildings on computers?
The reason why physical testing is such an important research tool for understanding the behavior of buildings and their components is largely due to the complexity of these structural systems. We can simulate or write a mathematical expression which might help us understand a beam, but that beam, when it's spanning from point to point, multiple points, or is clad or supports a floor system, becomes much more complex.
What kind of improvements to our codes and the way we design buildings has research like yours led to?
And ultimately, if we can model these systems to a greater level of precision, we can design them to a greater level of precision. So there is an indirect connection there, or direct connection there actually, to the improvement of design codes because the tools are improved for design engineers.
Where do you see physical testing making the biggest contribution to resilience in years to come?
One of the biggest challenges, I feel, is dealing with existing building stock. The engineering research community kind of needs to keep up with that and think of some more innovative strategies for rehabilitating and retrofitting these structures. And we talk now today as a research and practice community about functional recovery. We can't do that unless we address the existing building stock.
As impressive and useful as physical testing is, it can be expensive and will never be able to fully test the largest structures or how the full variety of existing structures might perform in earthquakes. Fortunately, with vast advances in computing, software and tools are now accessible to almost any engineer or researcher to test our theories and simulate designs much more economically at the desktop and with the computing power of the cloud. I spoke with one such researcher who is at the forefront of using computer power to help engineers design better performing buildings.
Well, my name is Kurt Hazelton. I'm a professor at California State University, Chico, and I also founded a software company, Hazelton Baker Risk Group, with a professor at Stanford. And we focus on software to support resilient design of buildings.
When I started out in engineering back in the late 1980s, running a computer simulation of a building often took all night. Things are sure different now.
So we can run 5,000 to 10,000 simulations of how your building might be damaged in an earthquake, and that takes 2 to 3 minutes these days. We've actually run, resiliency assessments of all the buildings in the state of California, 13 million. And with all of the Amazon processors that we can spin up, that takes 4 days to run all of that analysis. So it's amazing how much that stuff has improved in the last approximately 10, maybe 15 years. And really is a game changer in being able to do this kind of computing and analysis.
How has computing kept up with engineering science and our learned experience in past earthquakes?
Over the last about 20 years, we've gone from being able to design buildings for safety objectives to being able to evaluate buildings looking at damage and looking at damage to individual components in the building and doing that in a very complete way so that engineers can design to limit that damage and to get buildings to be functional more quickly after an earthquake.
A professor of mine once said, "Garbage in, garbage out." How do you verify that these sophisticated computer models reflect how buildings actually perform in earthquakes?
We do use earthquake data to make sure that we validate our predictive models. So one thing that we've done recently is we went back through and we estimated the damage and repair cost to all the buildings in Northridge in 1994. And we compared that to the Northridge experience data both in terms of repair cost, but also in terms of the likelihood that a building will be closed, be red tagged and deemed unsafe after the earthquake. And we found good agreement, and in doing so, we made some modifications to the method to tune some stuff up. And then now that we've done that, what we can do, since it's an analytical method, we can now forward predict using that same method to things that we don't have earthquake data for.
How are engineers using these software tools to design better buildings?
We now have the technology, right, or analysis capability to be able to do those designs, and to be able to say, if you make these 6 design decisions to make the building better, the outcome is a building that is quickly regaining function after an earthquake.
Are engineers using this technology to retrofit existing buildings as well as for designing new structures?
Yeah, this is not scoped to only new buildings. In fact, probably most of the uses of this technology are for existing buildings. It's the common use case is an owner, right, wants to know what they're getting for their current building. Is it going to be functional after an earthquake or not? And the follow-on question often asked is, what can I do to make my recovery time faster, right? What kinds of retrofits can I do? So this technology can be used for all of that.
Private industry innovators are also using physical testing and advanced modeling to create construction products and approaches that bring high technology cost-effectively to the job site. I spoke with 5 members of the U.S. Resiliency Council's Industry Partner Committee about how their companies are making better building performance more accessible.
My name is Alan Klemchek. I'm the president of Taylor Devices, structural products, and our products are used throughout the world to protect buildings and bridges from the harmful effects of wind and earthquakes.
Hello, my name is Kyle Wilson, and I work as a regional engineer for Side Plate Systems. So we created a patented moment frame design to be a direct solution to some of the design flaws that we as structural engineers found from those pre-Northridge moment frame connections.
My name is Blake Ross-Kelly. I am senior structural engineer in business and product development with Clark Pacific. Clark Pacific is a prefabricated building systems designer, manufacturer, and construction company. And we create building products out of primarily precast concrete.
I'm Brad Saxey. I'm the technical director for Core Brace. We are a manufacturer of buckling restrained braces. These are products that are used in buildings in moderate and high seismic areas to improve their seismic performance.
I'm Jeff Ellis. I am a licensed California structural engineer. I've been with Simpson Strong-Tie now for 21 years and manage our building code and product compliance efforts. Our company has been around since 1956, providing solutions for the construction industry since then, starting out with wood connectors and evolving into all the way up through moment frames.
It's often in serendipitous ways that new technologies and innovations come about. In the construction industry, oftentimes we learn best from what went wrong in the past.
It's interesting to see how structural engineers used to design buildings back in the 80s and in the 90s, and what significant earthquakes have happened. Side plate was developed in 1995, right after the Northridge earthquake. And from that significant earthquake, that's when we, as structural engineers, learned a lot of design flaws.
The kind of work that Tara Hutchison and Kurt Hazelton do is also being done by private sector businesses, from startups to construction industry giants, who are testing and modeling the behavior of materials and new approaches before an earthquake does.
From a product supplier aspect, research and development activities, design and detailing software, manufacturing processes, all of these things have significantly changed. We've gone from manually running and measuring, small component tests to performing tests using advanced electronically controlled hydraulic testing systems.
The software changes have been equally as important. Over the last few decades, the technology has grown exponentially. But additionally, the fact that many engineers use similar or the same software codes for building design is a key contributor to helping us integrate better resiliency in our products into structures.
Buckling restraint braces are an element that is highly tested, highly researched, a lot of full-scale testing, of analytical models. So this allows us to really understand how the building's going to perform and really optimize and tune the building for a specific performance that we're trying to get.
A lot of people may think concrete is a pretty low-tech material, but that isn't necessarily true, and it doesn't mean it's not resilient. Blake Ross-Kelly of Clark Pacific explains this, and also how their innovative precast hybrid moment frame works.
In a seismic event, the mild steel bars are allowed to yield while the strong tendon remains elastic, meaning it doesn't yield. So like a rubber band, it will bounce back as the building rocks back and forth. And because it remains elastic, when the shaking ends, it will pull the building back into place so that it is vertical again.
It's difficult for the construction industry to overcome the inertia that often sets in with contractors wanting to use the older, tried and true methods they've been employing for decades.
So we started working with structural engineers, getting them educated on some of the engineering benefits that it can provide to a new structure. And then from there, we used and leveraged those structural engineers to influence general contractors that it can actually benefit their project as a whole. Side plate is a very stiff connection. And so with that increased stiffness over a conventional moment frame design, we can actually reduce the overall amount of steel on the project from the steel beam and column sizes. And so that can equate to tens of thousands of dollars to maybe sometimes even hundreds of thousands of dollars, or even sometimes even $1 million worth of raw steel savings on a project.
Clark Pacific is a design build contract. The efforts that we go through are basically an education of our customer to let them know what the benefits are of a resilient lateral system and how the system performs in order to provide them with added value.
We offer a plethora of tools on our website for designers and installers and contractors, builders that are software type solutions, the ones that are on desktop that can help you design cast in place concrete anchors or post installed concrete anchors, or design moment frames, as well as tools to make the process more efficient.
Working with SidePlate in the early development stages, we offer a lot of free tools and free services up front in the early stage design so that the building owners, the GCs, or the design team can better evaluate and have the better education to determine what's going to make most sense for their structure.
Sometimes innovation comes not from having a high-tech mechanical system, but just from finding a better way to do the things we've always done in the past.
Really, innovation can be as simple as a screw that works more efficiently and is more effective in doing its job. And that can bring efficiencies to the industry, as well as perhaps creating safer structures.
We've talked in past episodes about performance-based design, the ability to achieve building performance beyond the minimum safety provisions. The technologies offered by these companies make it easier than ever to achieve high-performing structures.
You can reduce the amount of time it takes to occupy that building after an earthquake. It can reduce the repair costs. It can help to actually even reduce the acceleration of the things, the people, and the equipment that are in that building. So the owners definitely have a choice to say to their engineers, hey, look, I want a better performing building. I want my building to perform better in an earthquake. What do I need to do to upgrade my building so I exceed code requirements? That is definitely a decision that all owners could face, and that our technologies can be provided to give you that higher level of performance.
Are your products used both in new buildings and in seismically retrofitting existing structures?
Fluid viscous dampers are certainly applicable to both new and retrofit structures, for sure. We have now have over 750 projects worldwide that incorporate viscous dampers. And because fluid dampers act like shock absorbers on your car, they operate and absorb energy only when they move.
When you are changing the occupancy of a building, going going from a warehouse to a office use or something in the same building. If you're thinking about adding resiliency to the structure, that's a great time to do it.
In advancing the use of resilient design techniques, we have to address the situation and the needs of the building owner or developer. We return here to the case of the new Oregon Treasury Building, currently under construction in the state capitol, that we first introduced in a previous episode. A lot of construction in Oregon uses traditional steel framing fixed to the building's foundation. But because of the essential functions that occur every day within the Oregon Treasury Building, the project team decided to use base isolation to ensure that the building would be up and running after a major earthquake off the Oregon coast. Byron Williams, one of the project's managers, explains how the decision to use an innovative structural system was made.
The discussions around why base isolation provided that when steel did not really focused on what is the process that has to be used for that reoccupancy element. The base isolation enabled the post-event review just to be completed much more quickly. For us to be able to say that we wanted to be operational after that earthquake, the building was no longer the bottleneck in the process.
How did you show that the additional cost of base isolation could be managed? Did you look at other projects for guidance?
Yes. So one of the pieces that we did is we retained DCW Consulting to do exactly that for us. That they, at each of the stages of the design process, that they were looking at other projects of similar nature in those elements. So looking at base isolated buildings, looking at steel frame buildings, or whatever various aspects we were looking at, and helping us perform some cost comparisons to make sure we understood the cost impacts of different decisions, but also the likely ranges we were looking at kind of as we were just in some of those early discussions.
How did you communicate the building's expected performance in terms that the decision makers at the Treasury could understand?
So I think for me, one of the biggest tools that I used really was the USRC rating structure. Prior to really engaging with that model, I struggled to figure out how to articulate clearly the benefits and the different impacts. The framework really provided a mechanism to break it down into talking about damage to the building, the safety of the employees, and that recovery objective.
I assume that having a USRC rating also creates a level of consistency among engineers and the state going forward on future projects.
That science backing is really where it stands out, is that it's a lot of systems, they're more subjective in how they design those systems. And with the USRC system, the criteria were there that at some point you can hand it to, I could pick up from one structural engineering firm to another. For me, that was important. I want my outcomes to be repeatable by somebody else doing that analysis.
Innovation is a never-ending process, and the next generation of structural engineers and entrepreneurs are already thinking about how to improve the built environment. I spoke with Dr. Anahid Behrouzi, an assistant professor of structural engineering at California State University in San Luis Obispo, about how she is motivating her students to think about the future of resilience. She told me about one example, how Cal Poly's Earthquake Engineering Research Institute student chapter participates in a seismic design competition every year.
So the ERI Seismic Design Competition is an international competition. So they have to build a prototype balsa wood structure. It's about 5 feet tall. So what they do with that structure is they test it on a shake table. I do believe that this is one of those competitions that bridges the theoretical that they learn in the classroom with what is reality. We don't want them to be kind of in a bubble of academia. And it really resonated with them that, sustainability is not sustainable without resilience.
What are you doing to make sure students are skilled and ready to realize the possibilities when it comes to making our world more resilient?
We've talked a little bit about resilience from the design perspective when you're starting on a project, how building up that ability to communicate not just ideas, but having a similar resilience objective between the architect and the structural engineer is important. I think What we're trying to do here at Cal Poly, but the relevance extends to industry, of course, is that we are trying to take kind of different silos of knowledge. We're trying to take architecture, we're trying to take new design, seismic design and other types of hazard design, but also this idea of retrofit and bring them together. In terms of resilience, like, we just don't have the luxury of time to figure this out later. I think it has to be a very kind of forward-thinking kind of approach.
Failure to invest in resilience now will cost us dearly in the future. But as experts in this episode have shown, the state of knowledge, techniques, and construction practices have advanced tremendously in recent years, making resilient design more possible and attainable than ever for both existing and new buildings. Engineers are at a pivot point in their capability to deliver a more resilient built environment, but they also have to communicate that capability and encourage demand and the follow-through from their clients and our communities. I hope you consider what all this means for you, your business, and your communities. You can watch or revisit other Resilience Advantage episodes that address other aspects of the resilience movement, such as the benefits of retrofitting. Our next episode goes deeper into the growing use of building rating systems as a tool for assessing, communicating, rewarding, and developing policies to increase resilience. Thank you for joining us on the Resilience Advantage.
Well, thank you. I hope you enjoyed that episode. It was a fun one to make. It's been fun to talk to a lot of these innovators, actually tour some of their facilities, see these tests and shake tables in action. Of course, the funnest thing was to go and watch that Cal Poly engineering team shake that building, that little model of the building, on a mini shake table. You can see that there's just a lot of enthusiasm, a lot of great innovation, a lot of great entrepreneurship that's going into making construction high tech, right? And so I want to thank all of the folks on that interview or on that episode for being a part of the series. And now I'm excited to introduce our 4 panelists for today, where we'll be talking more in depth about some of these issues and how they relate to things like policy and design of buildings today. First, I'd like to introduce Lakeisha Woods. She is the President and Chief Executive Officer of the National Institute for Building Sciences. She'll tell us a little bit more later about what NIBS does, but it really is this fantastic national-centered organization that works on a whole range of topics. We work with her on disaster preparedness and disaster resilience, so I'm really excited to have you here with us. Our next panelist is Dr. Christine Goulet. She is the Executive Director for Applied Science at the Southern California Earthquake Center, SCEC. There's an acronym for everything, just so you know. So, and she and her organization and SCEC work to really understand the science behind the earthquakes themselves. Obviously, when we talk about building resilience, we think about the building, but obviously the earthquake and the types of ground motions and the intensity and duration and the likelihood, that's all critically important to know just what kind of hazard we face. Steve Marusic is a friend of mine and a structural engineer. He's a principal and director of technical excellence at Farrell Elsesser Engineers in San Francisco. And Steve has used a lot of the different types of technologies that you saw in the episode. And so we're looking forward to having him talk a little bit about some of the projects he's worked on. And of course, we're also happy to have back Dr. Ross Stein, who did that great demonstration, the CEO and co-founder of Tembler. So Ross, thank you for agreeing to be on this panel with us. So with that, I'm just going to start right in, and as I ask each of you questions, obviously I'd love to have you introduce yourself and give a little bit of background to what you and your organization does. So let's start with you, Christine. Why don't you tell us about the Southern California Earthquake Center, its mission, and what your role is?
Great. So SCEC is a consortium, a large consortium of different universities and institutions that coordinate earthquake research. We're headquartered at the University of Southern California. However, we have 20 core institutions across the country and over 60 participating institutions, also including the international level and so on, and over 1,000 researchers working together to try to better understand the science behind earthquakes and so on. So we gather data, we conduct research, we develop theoretical models, some more practical models, and so on. Then we use these models to test or improve knowledge of science. And then after that, we communicate our results of what we learn from all this work. We communicate that through, of course, scientific articles, and of course at conferences and so on, but also with stakeholders, including groups and committees of the building code, for example, because the ground motion is at the base of the design for seismic design. We also have a very active communication, education, and outreach group that runs the Shakeout earthquake drills, so you may have participated in it. And they also run several activities through the Earthquake Country Alliance banner. And so it reaches more the preparedness. So with those two aspects, SCEC is really doing research, but also helping communities to prepare in terms of preparedness. And that's SCEC in a nutshell. And as the director for applied science, I'm one of the persons that I'm the one who leads all the transfer of the basic fundamental science into potential applications to engineer. Being an engineer myself, I really care about the impact of ground motions on buildings, and that's really my role at SCEC, is transferring that scientific knowledge into more practical applications.
Well, that's wonderful. Thank you. And I'm going to follow up with a question that I get a lot. It talks about, how we measure how impactful an earthquake can be. You mentioned, obviously, that seismology is the beginning of earthquake engineering. You have to know what kind of ground motions are hitting the building. A couple of years ago, on Independence Day, almost 2 years ago now, I guess, the Ridgecrest earthquake hit in Southern California. It was a big one, too. It was magnitude 7.1. So it was actually one of the larger earthquakes by magnitude that we've had in California in, I guess, the past 50 years, probably. But, I heard that a lot of people in downtown Los Angeles, for example, didn't really feel it. Didn't really, they felt it, but it really, didn't seem like, wow, a big 7.1 earthquake. Now, you compare that with the Loma Prieta earthquake, which occurred back in 1989, so over 30 years ago. It was almost as big as the Ridgecrest earthquake. But even in San Francisco and Oakland, more than 50 miles away, it caused buildings to collapse, a whole freeway to collapse. So how is it that two earthquakes, say with the same magnitude, can have such different impacts on the people nearby?
So there's multiple aspects to that. And I think we need to start with not two earthquakes are the same. And we use magnitude to quantify the amount of energy released by the earthquake as it breaks the fault and it ruptures and so on. But if the rupture is fast or slow, two earthquakes with the same magnitude will have a very different type of shaking that we feel. So that's one thing. Another aspect is that if they have the same magnitude, again, we can have different behaviors in terms of ground motion. But if one is deep or further away, let's talk about deep first. So if you have an earthquake that's very close to the surface, that maybe ruptures the surface near your house, you're going to feel that a lot more than if it's, 30 miles deep, or in California, maybe it's going to go 15 miles or so. So that's because as the energy gets released and the waves travel to your side, they get attenuated over more material. So at the surface, where we care, where we have our infrastructure, there can be very large differences. Of course, different sites will have different response. So if you have a very soft soils in a place, it can amplify the motion. So the example of Loma Prieta, and if you remember the very traumatic vision I still have of the freeway collapse and Nimitz freeway collapse, this one was due to a combination of side effects and so on. So some of the pillars for the double-decker freeway were on stiff soils, we call, and the other one on bay mud that shakes very differently. So this differential shaking between the two caused the collapse, and that's something that's really important. So for these different reasons, that's why we design for ground motions and not for magnitudes. I often hear people, and when I participate in panels, people come, well, my building is designed for magnitude 7. I'm good. No, magnitude 7, what distance, what side effects, and so on. So the ground motion is really important. And even for ground motions, again, not two earthquakes are alike. And that's something we need to really accept and live with.
Well, thanks. Yeah. It reminds me of a story. I had somebody in San Francisco ask me if their building would stand up in a magnitude 7 earthquake, right? And I said, well, good news for you is your building's already been through a magnitude 9 earthquake and it survived just fine. The trouble was that earthquake was in Japan. So he didn't really like that answer, but
no, that's true.
So maybe I'll ask Ross, as opposed to being flippant and annoying. How do you find success in translating that sort of complex science of seismology and earthquakes into terms that your 100,000 subscribers to your newsletter understand and find meaning in?
Well, first, the first 3 rules of seismology are also the first 3 rules of real estate: location, location, location. And so more than anything else, what matters is whether or not that earthquake is underneath you or at some great distance. And people do understand that. And so the problem that we face is if we speak in terms of earthquake likelihoods, and then what we're doing is considering all earthquakes near and far, small and large, and then your building and your location and how they would affect you. And we would look at some amount of time, let's say 50 years, and say, okay, what's the largest you're likely to get? You're going to get some answer, and probably, fortunately for most of us, that's pretty modest. But then if we ask another question, which I think is the more relevant question to the population, is, okay, I live in Oakland. What do I really care about? No, I don't care about the probabilities. Just tell me what's going to happen to my house if that Hayward earthquake that the USGS keeps promising actually arrives. That's the question that individual will want to know. That's not probabilistic. That's deterministic. Then we're taking a scenario of an earthquake that we think is likely or possible and asking the question, what would it do for me? And then you want to say, okay, here's the losses that you would experience, the financial losses and the potential injuries for that earthquake. Now let's replay it with a retrofitted building. What does that mean in terms of your safety when things aren't falling on your head? And what does that mean for your survivability financially because your building isn't falling over? And now we're talking to people with, if you like, a scientifically sound story that more directly relates to what they care about.
Great. Well, okay, so I want to ask Christine one more question then about, and Ross, you're please welcome to jump in as well. We often hear scientists talk about uncertainty. Right? We say earthquake engineering isn't an exact science, but really nothing is an exact science. The science is all about reducing uncertainty over time by the way we learn. But then they'll follow up with, well, if a scientist can't be sure about something, then why should I be concerned? And gosh, haven't we just heard all about that over the past year when it comes to the pandemic, right? So Christine, Ross, as our scientists here, why should the public be okay with uncertainty, and how should they factor that into their decision-making process?
So let me start with that. So to the general public, uncertainty means we don't know, we just don't know. That's not quite right. So for scientists and engineers, uncertainty is not a bad word at all. We know a lot of things. What we might not know is the exact value of something we're trying to measure. So we do understand a lot of things, a lot of physical phenomena. We can kind of predict them or model them and so on. So for example, let's take ground motion. We talk about ground motion from magnitude 7, 50 kilometers away on such soil and blah, blah, all those different parameters we consider. Maybe the values of ground motion span this range. You know, that's what we can expect. And there's some uncertainty. So it could be this value, it could be that value. We don't know exactly which one because there's some uncertainty. We want to know what that range is. And then we want to make it narrower, as you mentioned before. And why do we want to make it narrower? So it's a little bit like the example that Ross just mentioned. Imagine you want to put a building in a location. Location. If I tell you that the ground motions can span that range, once you integrate that to risk, to get, you need to integrate all the uncertainties, all those variabilities that we capture. Your risk in terms of dollars you can expect to spend in the next 50 years due to earthquake damage might be that wide. I mean, it can spend hundreds of thousands to millions of dollars for a big structure, a tall building. So how do you make a decision based on that? It's really hard. You can't. Are you willing to go to that risk, but you could have that low? If we reduce the ground motion uncertainty because we start to understand the physics better, we gather more data at your site, you put instruments and we know exactly what's going to happen, we reduce this, we also reduce your range of dollars you're risking. Then you can make the decision, yeah, well, this is too much risk. This is okay, but you're in a better place to make a decision. So the quantification of uncertainty is really critical, and it's impossible to make a decision without considering that. Because if I give you a mean number, these two have the same mean or average number, but they mean very different risk that you're taking. So what people like me at SCEC and other places do in research, we're really trying to quantify the uncertainty and reduce it by more knowledge, understanding, and physics. So uncertainty is not a bad word for us. And so we need to disconnect that from the public perception.
Thanks, Christine. Ross, did you want to?
Yeah, I had a very humiliating experience a number of years ago when we were working with a client at 185 facilities around the world. We said, look, we can give you a probabilistic look at your hazard worldwide. And we made a map that showed colored dots for all their locations around the world. And those dots were the amount of shaking that had a 2% probability of being exceeded in 50 years. This is a standard engineering term. And the people we were talking to looked at that and said, 2% in 50 years? We don't have a problem at all. Go away. And we realized, oh my God, we don't know how to communicate because these numbers sound like they will never happen. So one of the things that Temblor does is what we say to people is, this is the largest earthquake that's likely to happen in your lifetime, or this is the strongest shaking that's likely to happen in your lifetime. Now, technically, that's a phenomena that has a 1% chance per year of occurring, because if you live to 85, then you have about a 57% chance of experiencing that. And also it resonates with the world of flood, where if you live in a quote 100-year flood zone, a zone that has a 1% chance per year of occurring, you're actually required for your mortgage to carry flood insurance. So we're always looking for ways to make this personal and real. And the idea is, hey, if this is likely in my lifetime, I better be prepared for that. I don't have an excuse not to be prepared for it.
Thanks, Ross. Yeah, I mean, communication we've just seen the challenges over the past year, and it's something that engineers and scientists work on all the time to make sure that those that are actually making the decisions have the terminology, they have the data in the form that they best use it, that they're most comfortable with. That's always a challenge for scientists and engineers, is to reach people where they're at. But thanks, Ross, for that. So now let's move out of the ground. Let's talk about the building itself. So I'm going to introduce Steve Marusic. And again, he and I have known each other for quite a while. He's a lot younger than I am, but he's a great engineer, and I'm really happy to have him here. So Steve, why don't we start by just having you introduce yourself and tell us a little bit about what you do at Farrell Elsesser.
Sure. Thanks, Evan. Again, my name is Steve Marusic. I'm a principal and a director of technical excellence at Farrell Elsesser Engineers. We're a structural engineering firm in the Bay Area. We've been in business for about 60 years, and we focus a lot on seismic resilience, even before it was called seismic resilience, right? Improving building performance through smart choices and through new technologies. And that's one thing that's made our firm successful over the years. So, it's something we carry forward. And, as Evan mentioned, I think pretty much one of the presenters that talked in the video segment, we worked many times with over the years. So we're very familiar with their products and, staying on the cutting edge, working with researchers, learning from the past. We've had a lot of people travel to various countries to learn from earthquakes, which is very important for what we do, as Evan mentioned, but we're also looking forward. So we don't need to do everything the way we've done it in the past. We're always looking for new ways that we can improve performance and either, at little to no cost to our clients. And I think that's really an important part of structural engineering and the future of structural engineering.
Well, that's a good I'll follow up with that then, because that's a good answer there about always sort of looking forward and using new technologies, being willing to change the way we've done things in the past. I mentioned in the video episode that structural engineering is one of the oldest disciplines. We have built with the four materials of concrete and wood and masonry and steel for so long. Why should we bother looking at new technologies, many of them not really even that new anymore, for building design, compared to doing things the way we have done it in the past?
Sure, it's a great question. I mean, honestly, resilience has become much more of a topic that our partners and clients are asking about. And technology is a way to really help address their concerns. And obviously, in the Bay Area, it's a very high cost of living place. So anything you can do to improve performance and keep the cost minimal is going to be of very great importance to our clients. If you've a municipality and you have an emergency operations center that you need to have functional after an earthquake, or if you have high value contents at a university where you're studying, you have cell cultures that are worth, billions of dollars because they're one of a kind and you want to protect them, or even just owners who are looking long-term, right? Who are saying, well, I'm going to own this building for 100+ years. And I know that an earthquake's going to happen, right? We don't know how big and we don't know when, but it is going to happen. And we want to be prepared for that. We want to be able to reoccupy our buildings, whether it's a hospital or an education facility or some other function that really serves the public domain. And, obviously technology is one of those places where we can do more with less. I mean, base isolation, we've been working with that technology since the 1980s. I mean, generally it adds 1% to 3% cost to your total project for a new build, which is really fairly small in the grand scheme of things. And a lot of times you can find ways to offset those costs by, being smarter with some of the other design decisions that you make to the point where it can be, neutral or nearly neutral. Other technologies like passive dampers or BRBs, I mean, essentially those are almost common in the lexicon today. And they have little to no cost impact on your building. But that's really the biggest hurdle, is really overcoming this perceived cost increase that really has to be addressed early. And just the fact that we can show either our projects that we've done or projects that other firms have done that, look, this has been done before, it's been successful, it's been constructed, the costs were very minimal. I think those are things that we can do to really help push the industry forward. And there are those communication tools that I think a lot of people have talked about in terms of whether it's the USRC rating system or other systems to really help take the engineering speak into something that an owner can understand. Well, how much better is better, right? What is the value I'm getting out of spending these dollars? And then they can do an ROI of their own to determine if that's the right decision for them.
That's wonderful. Well, now we can come out of the building and really talk about how owners and policymakers make decisions about individual buildings, long-term strategies. And so that's why I'm really excited to have Lakeisha Woods here with us. I have worked with NIBS off and on over many years. Way back in the day, I helped work on the HAZUS program, which was one of the big projects that NIBS worked on in the late 90s. But Lakeisha, why don't you introduce yourself, please? Tell us a little bit about what NIBS is and what the kind of projects it works on around the concept of reducing impacts of natural perils.
Sure. Well, thank you. Again, my name is Lakeisha Ann Woods. I'm the president and CEO for the National Institute of Building Sciences. NIBS was created by Congress back in 1974 in an effort to align the building industry. We are conveners. Our job is to look at the industry and make sure we're utilizing the best of sustainability and technology when developing the places where we live, work, learn, and play. So NIBS is a great group. We have members that are both associations and also practitioners, architects, engineers, code officials, building owners. And our job is to align all of those groups and ensure we're looking at areas where we have common challenges and how to find solutions. I think the groups you're most familiar with are two of our councils, the Multi-Hazard Mitigation Council, which is very well known for our report, the Mitigation Save Study, and then also our Building Seismic Safety Council that works on the NEHRC provision.
Well, good. I'm going to ask you about the Multi-Hazard Mitigation Council and Mitigation Saves. So for those of you that don't know, this has really been a landmark publication. It was produced several years ago, is recently updated. And you will hear this publication quoted by professional engineers, by business owners, and you will hear it often quoted by our nation's leaders in Congress and in other departments. And, you know, at its heart, Mitigation Saves makes the case that when we invest in resilient design or mitigation of existing, you know, older structures, we can return huge benefits. For every dollar spent, we can return 3, 5, even 10 times the cost sometimes. So, Lakeisha, I'd like to ask you why it was important for NIBS to conduct such a study, to have this kind of information and to use it to advocate at the national level for resilience.
Absolutely. Well, the study was started back in 2005 when Congress asked FEMA if the agency's mitigation grants were a good investment. And NIBS came in and did the report, and we concluded that what is now very well quoted, the 4-to-1 benefit cost ratio. However, as you mentioned, we've redone the study. We did it, I think, in 15, 17, and 2019. And our recent mitigation save studies have served a similar purpose, but with a broader impact. And we were really pleased to see the findings. They've been used to support some of the most significant policy changes, like the new FEMA BRIC, Building Resilience and Infrastructure Communities program, which has really stepped up the federal effort on mitigation investment. And you'll probably hear it often quoted that you can save up to $13 for every dollar invested in mitigation. And we also did another study for the Portland. They were looking at doing a resilient runway, a seismically resilient runway, and it actually saved Portland. It will save them $50 for every dollar invested. So it's really important to look at mitigation, and especially as the other speakers have quoted, the cost in comparison is really negligible.
Well, yeah, and that 13-to-1, by the way, is for seismic mitigation of older existing structures. So all of us that are out here on the West Coast, you're really getting a bang for your buck doing that. So, okay, well then let me follow up with a question about, we've heard a lot about this current administration's plan to, quote, build back better, right? This idea that we should be building resilient infrastructure, we should be repairing our infrastructure, making it resilient and hardened to climate impacts. How do you see yourselves, but also the greater sort of engineering and science community contributing to making the case for resilience as part of these sort of build back better strategies?
Sure. We've actually sent communications to let the administration know that we are here to serve as a guide. Many people know that of our board of directors for NIBS, 6 of our board members are appointed by the President of the United States. And we actually have 3 new board members who will be brought on board, and I think actually 3 more to come. So we're really excited about the changes that have been happening within the administration. Now, as you're referencing, this is a big initiative that's really led by our subcommittee of MMC called the Committee on Finance, Insurance, and Real Estate. And it's a white paper. Basically, it was motivated by our natural hazard mitigation save study. And the question is, if mitigation saves with returns of 4, 6, 11, 12 times the cost, what's next? How could we increase more mitigation activities? How could we really, truly create a resilient economy? And that is what the Resilience Roadmap white paper is really trying to answer. The mission of CFIRE is to support building sciences, finance, insurance, and real estate, and to have a mutual understanding of how we can work together to improve the industry. We want to connect improved engineering design, which leads to better codes and standards, which of course in turn leads to better financial products and insurance programs. And there's so much opportunity ahead of us.
Thank you. That's great, Lakeisha. And I'm gonna come back to that other white paper. I'm kind of a groupie when it comes to reading NIBS's white papers on resilience. So, but Steve, let me just come back to you and ask you. You had mentioned this previously about achieving resilience at minimal cost, typically, especially when it comes to new buildings. But what kind of tools? And this is sort of a question about how the engineering profession, yours and I's, that we started in many years ago, how it has evolved to be able to talk to owners, as I mentioned before, in sort of terms that they get, that they understand. What kind of tools and communication means do you use to talk to your owners about things like return on investment or benefit cost analysis, why it is worth even investing a couple of percent into innovative technologies and high performance?
Sure. Yeah, I mean, that really has been one of the breakthroughs, and it's not necessarily new. Seismic loss estimation has been around for decades. But the analytical tools that we now have available, the computing tools to really simulate buildings and to simulate a building's response to an earthquake and really understand where we think a damage will occur for an existing building, for an example. Then we can develop retrofit concepts that address those. And by then taking that and using some of the new FEMA P58 type analysis software, whether it's SP3 or something else, or the USRC rating system, then we can quantify, okay, how much do we expect the repair cost to be? How long will the building be down? And then that will give them an opportunity to look at various scenarios. So we can say, all right, the basic retrofit would look like this. And then your repair cost might be 20, 25% of the replacement cost of the building. Or if we do one of these 2 other things and we add a couple more things, we can bring that down to 15%. And going from 6 months of downtime, you can go to 2 months of downtime, essentially. And then they can use that to look at, okay, it's a way for them to understand how much better is better, which engineering speak just was never able to really produce. But most clients understand dollars, right? So they can look at, okay, repair costs goes from $2 million to $4 million, and my initial investment is only $500,000. That's a pretty good, as Lakeisha mentioned, if it's a 4-to-1 benefit, okay, that's something I should seriously consider. And I think just certain analytical tools, a lot of work that's happened in the community at the federal level and kind of state and local levels have really helped us. Have helped give us communication tools that owners can understand, and with help from cost input, they can really make a decision that's right for them based on all the facts that that they need to do that.
Well, so I know when I started, it was pretty rare to use some of these newer technologies. In fact, I think. Although I worked at a competing firm, Farrell was one of the first companies in the Bay Area to use base isolation on a project that I recall. So nowadays, I mean, versus say 20 years ago, I mean, what percentage of your projects, new or retrofit, employ some kind of sort of newer advanced technology?
I'd say at least, a quarter of our projects involve something, whether it's advanced analysis or a new technology like base isolation. I mean, we have half a dozen projects in our office right now that are base isolated. We have a few that we're looking at passive dampers, BRBs. We do every day. We're doing a few of the precast hybrid moment frames that Clark Pacific mentioned for various clients. So, I mean, it really is there. I think retrofits generally provide a better opportunity because they're usually unique and constrained projects that require creative thinking and innovative solutions. And I think clients are usually more open to pushing the envelope a little bit more than a new design where, perhaps first cost is the most important driver for them. But again, I think a lot of it just comes back to education. And if we can lay out options, I mean, some of our projects, we've shown that innovation systems have actually saved money over conventional approaches. So it's not always that things have to cost more. They may actually save costs. So I know we always keep talking about cost, but that's generally the hurdle that most owners struggle with is, resources are limited. And especially if you're a large portfolio client and you have to retrofit a lot of buildings, existing buildings, then you can't afford to overspend on any one building because that means something else may not get done. So those are the cost pressures that really drive a lot of what we do. But yeah, it is important to understand that, they're all out there, and many firms have similar experiences where that's where having that community is important, where whether it's we've done something that's first or whether somebody else has done something that's first, it's always helpful for an owner to understand that it's been done before. Sometimes we don't want to be the first out of the gate, but second is great. So if you can't be first, then at least drawing on the work of others is important to kind of just keep driving the mission and the purpose of resilience, because I think there's as Ross mentioned, right? You just want to know how it's going to affect you, right? If you're a homeowner or a building owner, you may not be necessarily thinking about the community at large, but just look at what happened in Christchurch, right? In downtown, and, for damage reasons, insurance reasons, I mean, they essentially scraped the whole downtown area almost, and, they're rebuilding. And, is that something that we want to have happen to the Bay Area or Los Angeles or anywhere else in the country, whether it be earthquakes or other natural disasters? And I think the answer is no. And that's where education of the general public is also going to be critical, because I think owners are one thing, they can understand it. But I think the misconceptions of what the building code does and doesn't do is still something that as a community we're struggling to overcome the inertia that, well, my building was designed to code, so I'm good. I think.
Well, and we've talked a lot about that in past episodes, about sort of what the code was designed to do, what current codes are designed to do, and of course, the fact that we've had to improve our codes over time because of what we learned in past earthquakes. We have a question from the audience about digital twin technology. And I don't know if Pharrell has used this at all. I know that it can be used oftentimes when you have an older existing building for which you don't have any drawings or plans, and you use this kind of technology to sort of capture existing conditions. Do you, or any of our panelists, have you used digital twin technology? Can you talk a little bit about that?
I have not personally used it, so I'm not sure I'm the best to answer that question. But I mean, it is something that comes up a lot where buildings have no drawings, or then you just do the best you can. Whether you can take digital surveys of a building to really understand kind of how it's put together. But if anybody else has anything to add, I'd definitely be interested to hear what they have to say.
All right. Well. If not, then let me just ask Lakeisha. I know that we talk a lot about buildings, obviously. Buildings are critical to a resilient community, but the things that serve buildings are also just as important. If you can't get to a building, you don't have utilities that serve buildings. I know that NIBS does a fair amount of work with lifelines too. I thought maybe you could talk a little bit about what you're doing on lifelines.
Yes, absolutely. Well, we've talked a lot about it. We recognize that the national infrastructure is varied, it's complex, and it's critical to life safety and national welfare. to such an extent that the entire system of systems is termed lifelines. These lifelines include energy, electric, gas, liquid fuels, renewables, transportation, roads and highways, rail, air, water, communications, telecom, internet, water, wastewater, emergency services. You know, what's interesting to me is in the 2.5 years I've been in this role with NIBS, I had a conversation with one of our agency partners, and they reinforced the importance of NIBS because they said that all of these various lifelines, they don't talk to each other. They are set up to create codes and standards and processes for their own individual lifelines. And that's why it's so important for us to take action. The risk governance varies by sector. It's often self-regulated, where federal agencies or public utility commissions have regulatory responsibility, but the risk often goes unaddressed due to lack of technical resources. So responsibility for risk management often falls to individual utilities, and they really lack the capacity or broader perspective necessary for a nationally resilient infrastructure. The result is an uncoordinated and wide variation in infrastructure risk management across the nation, with often unacceptably low disaster preparedness, as evidenced by the numerous infrastructure failures in recent disasters. Siloed risk management also leads to under-design, where the responsible owner or operator focuses minimizing first cost, and as a result, externalizes the risk of catastrophic future losses for the rest of society. And we know it's the public tax dollars that pay for this. We need an umbrella lifeline organization to align all of those various lifelines and to be a steward for research, development, and implementation of resilient lifelines. And that is something that NIBS is very focused on, and we hope to work to put that in place.
Yeah, thanks, Lakeisha. It is, and this is I'm going to follow up with a question to you on this, but it just shows how resilience isn't just one person's issue. Everything is so interconnected, from our buildings to the lifelines, to the services, to the resilience of the people in a community itself, are the financial considerations around all of this. And our part in the Resilience Advantage series is to focus on one aspect of it. But Lakeisha, as you say, it is so interconnected. And that's why groups like NIBS and the U.S. Resiliency Council and so many other organizations are trying to see the intersections, right? And the places where we have common purpose and common goals. And so I'm going to follow up by asking you about another one of the MMC's white papers, and this is called the Incentivization White Paper. And this white paper basically laid out the idea that when you mitigate a building or you design a building to a higher performance level, make it more resilient, a lot of folks benefit, right? It's not just the owner who's benefiting from having a building, that the asset that will be protected or their business will be protected. The tenants of the building, if there are tenants, benefit. The city and counties benefit from having, a tax base, even if it's simple as a sales or a property tax base that'll be maintained. Lenders and insurers benefit. Lenders benefit from having reduced risk of the property going into default. Insurers have less risk of paying out claims after a natural disaster. And so what really intrigued me about this paper was it laid out the case that you can quantify those benefits. And then if you can quantify the benefits to all these other stakeholder groups, then you should be able to encourage them to pay for some of the costs, right? So that the owner of the building isn't the only one that has to foot the upfront bill, even if it's only, like Steve says, just a couple of percent. That can still kill the resilience on a project. So all the folks that receive benefit should contribute to the cost. So maybe you can talk a little bit about the kinds of incentives or the kinds of policies that NIBS is advocating for around sort of sharing the burden of resilience to all the folks that benefit.
Well, and I know that within the audience chat, the mitigation saves report and this incentivization white paper is already, there's a link there. So please feel free to take a look at the materials that are available. Our goal is really just to align those various industries, those stakeholders, like you mentioned. We are pushing for just that, to ensure that we're bringing all the people to the table and ensure that they are sharing that cost so that we can make better decisions. As I had mentioned earlier, and I know I kind of got into this piece of the conversation early, we want to connect that improved engineering design, which again leads to better codes and standards, and then again, better products and insurance programs. Engineers are doing a brilliant job to advance our design practices, but many times it's not necessarily to be able to communicate the value of improved design to other stakeholders, like lenders, like insurers or building owners. So it's important to understand how to build and how to evaluate. Those are the key questions that both the engineering and science community will need to help promote incentivization. And I know that your organization, USRC, is leading some of these important efforts in rating our buildings.
Well, that is wonderful. Yeah, it is one of our core goals is to find ways to promote resilience through incentives. Christine, I'll bring you back into the conversation because I know that SCEC also has a role in communicating resilience broadly, sort of on a societal level. Maybe you can talk a little bit about what SCEC does in that regard.
Yeah, so we're currently planning a very large workshop, and so maybe the link can be shared with the people who are attending. But on June 7, 8, and 11, we are hosting a workshop that we call Societal Shock Resistance. So it's a big name. We replaced a very long 20-word proposal title into those 3 words, Societal Shock Resilience. That's funded by the National Foundation. And with that workshop, we want to get at how we can improve the resilience of society as a whole, not just the building, but really society as a whole by working together. And this issue of really coordinating across different fields is really important. And Lakeisha really expressed that well in the case of Lifelines. So we define society as a complex system of systems. And at the biggest level, we can think of the natural environment, the built environment, and more importantly, the people. So that built environment, of course, includes the buildings, the lifelines, communications on the health systems as a whole need to communicate the same way that Lakeisha talked about the resilience among utilities and so on. So, and the shocks we're considering in that workshop include earthquakes, of course, because that's what we do, but also hurricanes, fires, even pandemics. So the workshop is really meant to gather broad community input from stakeholders and different aspects of resilience, from the hazard quantification, the mitigation, the design, the vulnerability, and all those different aspects, by also talking about policy, equity, and all that is really relevant to the big problem of resilience to shocks such as earthquakes and so on. So we're also inviting stakeholders. So people who represent different communities, it could be small business owners, people who are in the nonprofit realm that represent specific communities, to join the workshop so that we gather their input into what we're producing, which is going to be a summary of the next key issues we need to resolve to have an impact within 3 to 5 years. So it's a very fast-paced concept for this workshop. But what we expect outside, and in addition of the NSF, program that is leading this workshop, is really building broader communities to facilitate those communication among the different stakeholders and expertise. So I invite you to go look at the website and read more about the workshop and register. We have 1 more week, actually less than a week to register. But we welcome you to join us and be part of the conversation.
Give us that website again.
So if you go to scec.org and in the search bar you put resilience, it's going to bring you there. I shared in our internal chat here the link. So so you can share that link maybe with the attendees Yes, so Cheryl said she put it in the chat.
Great.
But we welcome engineers, social scientists, communicators, policymakers, land planning specialists, really, and even politicians. We want all the people to have an input on what needs to be done for the global resilience.
Well, I think that really speaks to, and I know it's the work that you have been doing, the work that NIBS does, is this idea that it takes a large village, and meaning it takes, to get real systemic change, you have to have input and buy-in and the expertise from all of these different groups, public, private.
And, yeah. And you need the interface between them. We need to speak the same language and exchange the data so we can connect the dots and not work independently. So.
Thank you. Well, before we finish up, let me just ask Ross and Lakeisha. Ross, what's new? What's the next great thing that you're going to work on besides your, IKEA folding building? What do we have to look forward to from Tembler?
Well, I want to slightly switch and say, I'm talking to these great engineers, to the head of NIBS. Here's what I think we should remember. Why is it that it is safer to drive to the airport than fly across country? In fact, it's safer to drive to the airport than fly to Europe. And the reason is aircraft black boxes. That for 50 years, every single commercial plane has been instrumented. And when anything happens, any issue at all, it's analyzed and the plane or cockpit communications is redesigned. So we understand what happens in accidents or incidents, and it's rapidly attended to. And today, more than 50% of the new cars on the road also have a black box. It's called telematics. And that's why that if you buy a car that was built in the last 3 years, your chance of fatality is 5% lower than just a 3-year older car. And that's because all of the driver activities and car responses are analyzed in these black boxes. Now let's compare that to buildings. How many buildings are instrumented seismically so we understand how that damage was related to the shaking that propagated through the building? It's less than 1.1%. So we are leaving our buildings without black boxes. And if we want to make changes to drastically reduce the cost of making buildings stronger and understanding them better, we need to instrument buildings. What we've heard about in this wonderful presentation about shake table modeling and component modeling is also valid. But it seems to me this is what's missing in what we're doing, and it's rectifiable, it's remediable.
Thanks, Ross. Yeah, well, in having 3 teenage boys, all that drive, believe me, I won't even touch a car that doesn't have every fancy lane assist, backup sensor, all that kind of stuff. So I hear you. Lakeisha, what is up with NIBS? What are new initiatives that you're working on?
Well, one, I have to comment because the fact that Ross just mentioned that, I was speaking on a panel last fall about the importance of building codes. And that was exactly the message that I gave. I compared our industry to the automobile industry because I had recently gone with my husband to purchase a car. And they went and they knew we had a young child and they shared all the safety features of the vehicle. They told us about how safe, and why we needed to spend this excessive amount of money on a vehicle that had every safety feature that made us feel comfortable. And of course, we bought it because we trusted all of those safety features that they sold us on. It was an important message. We spend far more time in our homes, especially now, than we do in a vehicle. But when I went to buy a home a year later, no one told me about the safety features of the home. They didn't tell me why it was so much safer because it was built to code or any of that. They told me about the countertops. They told me about the neighborhood location. But it was amazing to me how our industry fails to sell the message, to tell the story of the importance of building our buildings, our homes, the places where we live, work, learn, and play with these safety features that don't just, right now we make it so that you can build to code so that you can get out alive. but we need to build to a higher code so that you can not just escape safely, but so that you can go back in and continue to live and thrive. Because what kind of life do you have without a place to live, without a job? You need that infrastructure, that shelter, and we need to sell the country on why it's important. And telling those stories, people will always be willing to invest more. If we tell those stories better, the people on the Hill can do their job better. So we as an industry must come together and do better at telling our story. And in doing that, NIBS is doing a lot of great things as we move forward. Of course, we are preparing for the next iteration of the NEHRC provision, but we're also really actively involved in working towards equity in our workforce. And so that is something that is important and that we are driving some initiatives on. We are putting together various stakeholders for our U.S. national BIM program, and we've convened experts from across the various stakeholders, just like we've talked about today, to bring owners and agencies and all the various engineers and architects all in the room together to talk about how we can truly not just find a solution, but a solution that everyone will use, because the silos in this industry are plaguing us. And until we stop trying to do it by ourselves and we learn that we have to work together to improve everyone and the industry as a whole, that's when we're going to get to where we need to be. So I'm very excited about the work that's coming up for NIBS. And of course, you can learn all about it and a lot of other great initiatives at our upcoming annual meeting in September. So we've got a few months, but just go to nibs.org and you can keep in touch with all the great things that our team is working on.
Thanks, Lakeisha. Well, thank you to all our panelists. We're reaching near the end of our time, and I think we could keep talking. But boy, Lakeisha Woods, Dr. Christine Goulet, Steve Marusic, and Dr. Ross Stein, thank you so much for your insights today. It was really a pleasure to speak with you, get to see you, some of you again. And, thank you for everything that you've presented. With that, I just want to again thank you for thank you to our promotional partners. We couldn't do it without these folks. These partners have helped us promote, provided us with science and graphics to help, spice up our series. And they've really been great champions to get the word out about what we do. So again, a big thank you to all of them. Now, so if there's one takeaway that I'd like to make sure that you have from this episode and that you really embrace, it's that science and innovation have and will continue to achieve great advances in our ability to forecast natural hazard risks, predict building and performance when they're subject to these hazards, and protect our buildings and their occupants when the hazards hit. We know that earthquakes are inevitable in California and other parts of the world, but they don't have to become disasters. And with the innovations in software and hardware that you've learned about today and the kind of research that's being done in universities and in these organizations, engineers and builders continue to be able to better protect our businesses, our economy, our communities reliably and affordably. So I hope that came across to you today. So with that, I would really encourage all of you to continue following the U.S. Resiliency Council. Love to have you as members of the USRC. You can check out our website and find ways to join and contribute to the USRC. And we're excited about our upcoming episodes. On June 16th, our episode is on rating systems. June 19th. Our episode is on rating systems and how they deliver resilience. And then in July, we have an episode on policy and incentives directly. Okay, this idea of how we move policy forward and promote financial and other types of incentives to make resilience happen, as many of the folks today spoke about. So with that, again, I want to thank you so much for your attendance today, and I hope you enjoy the rest of your day.